Hi everyone, welcome back. In this video, I'm going to discuss about the most widely used asymmetric encryption algorithm, which goes by the name as RSA algorithm. It's called as, it is actually named after the three people who actually invented this algorithm. Those three scientists are Rivest Shamir and Leonard Edelman. So these are the three guys who actually came up with this idea. And this is one of the most prominent algorithms that has been used in the domain of asymmetric encryption. If you remember, as we discussed earlier, we have two branches of security. One of them is the symmetric encryption scheme, and the other ones are called as asymmetric encryption. In symmetric encryption, we use the same key for encryption and decryption purposes. On the contrary, with the case of asymmetric encryption schemes, we use one key for encryption and a subsequent at a paired key, but a different one. Though it's paired one, we use it for decryption purposes. We'll see what that is, how these keys are generated, how it can be used. Okay. So the RSA algorithm is a prominent asymmetric encryption algorithm, which has been developed by these three guys and was first publicly described in 1978. Since it has been come out and been used for public usage, it is vastly used for many different types of applications. RSA is actually motivated by the published works of Diffie and Hellman from several years before, who described the idea of such an algorithm. They actually published a paper in 1976. We will discuss more about the Diffie-Hellman key exchange algorithm in our next video. So from that paper, these guys got the idea and came up with this algorithm, which can be used not just for key exchange, but also for encryption and decryption purposes as well. So the invention of RSA algorithm brings one of the significant improvements in the field of cryptography, which brought the usage of number theory concepts into cryptography. They started using the number theory concepts. We will discuss more about how they used and how we can implement both encryption and decryption as well. It is based on the presumed difficulty of determining the prime factors of a large number called the factoring problem. Here, if I give you a particular number and if I ask you to divide it into its prime factors, and if I give you a number which is large enough, it is quite difficult to do the factorization. That is the actual basis on which RSA is built on. That's what we call it as the factoring problem. RSA can be used for encryption and decryption purposes, as well as creating digital signatures. It has been extensively used in various applications ranging from financials, banking, even your e-commerce. A lot of things are there which are based on the RSA algorithm's usage. Let us discuss more about the particulars of the algorithm. So here, once again, the plain text is encrypted in blocks, with each block having a binary value less than some number n. We'll discuss about this n, what is this n, what is this value. We'll discuss more about it once we go into the details. The actual RSA encryption and decryption computations, so how you perform the encryption and how you perform the decryption, is pretty straightforward. There is only one calculation that we do, and it is nothing but a single exponentiation in modulo n. That's all. So you just perform one exponential calculation, and we do it in the modulus of n. Both the sender and receiver must know the value of n. The sender knows the value of E, and only the receiver knows the value of D. In a sense, in asymmetric cryptography, as I told you that if a particular user A is present, he will have one key called as the public key, denoted by PUA, and he will have a paired one, which is called as a private key, which is kept secret. Similarly, if there is another user B, he will have a public key called as PUB, denoted by, and he will have a private key denoted by PRP. In this case, both the users will share their public keys and keep their private keys secure. They don't ever share these private keys at all. Only the public keys of the users are known. So here, in this sense, in RSA, what this statement tells you is n is known to everyone, doesn't matter, and E can also be known. So the combination of E and N forms your public key for a user, and the combination of D comma N forms the private key. So here, though the values of E and N are known to everyone, it must be in such a way that an attacker should not be able to guess what the value of D is. should not be able to guess, or you should not be able to calculate the value of D, which is your private key. Now, to encrypt a message, as I told you, both the encryption and decryption computations in RSA algorithm are actually a single exponential calculation only, isn't it? So to encrypt a message, M, the sender obtains the public key of the recipient, PU, because as I told you, public key, there is no issue at all. We can distribute the public key to everyone. That is, hence the name tells you it is public key. So that is known to public. Now, PU is equal to E comma N, and then it computes the ciphertext, or it does the encryption such that C is equal to M power E mod N, where M is your plaintext message, which has a value less than the value N. That's what I told you here. Plaintext is encrypted in blocks, with each block having a binary value less than some number N. This is your N here, and this is your plaintext message M, which is to be encrypted, and this is the formula which you do, M power E mod N. This E belongs to the public key of the receiver. Now to decrypt the ciphertext, see, the owner uses their private key, PR is equal to D comma N. As I told you, the private key is kept private. You never disclose the private key to anyone. Only your public key is known to the users. And then computes M is equal to C power D mod N. Here also, if you observe, we are doing only a single exponential calculation with modulus N. Okay. So to understand this, let us see what happens at both the sender and the receiver. If two parties wants to now perform an RSA encryption scheme, how does it happen? What are the terms that they need to take into consideration? Let me do that. Let me show you. Even before going there, you have to understand that there are some certain requirements that the RSA algorithm has to meet for it to be satisfactory as an asymmetric key encryption algorithm. Now, if you see here, the first requirement states that it is possible to find values of E, D, and N such that M power ED mod N is equal to M for all M less than N. That means this should do as inverses. So M power E into D mod N is equal to M. And it should also be relatively easy to calculate both the calculations that I shown you earlier. This is your encryption calculation, M power E mod N, and this is your decryption calculation, C power D mod N, for all the values of M less than N. And the third one, which I also told you, even the attacker knows the values of E and N, which is your public key. It should not be possible at all for the attacker to calculate and determine what your private key is. That is your D. Now, let us start discussing what the ingredients are. What do we need in order to proceed on to perform RSA encryption? The first thing we need is two prime numbers, P and Q. P and Q are not equal. We should not take two equal values. The only constraints for selecting P and Q is P should not be equal to Q. And usually for practical purposes, P and Q should be very large. They should be having around 100 digits or more. Okay. So P and Q are two prime numbers which are private. So you do not disclose both P and Q to anyone. You choose P and Q. After that, then you calculate N. N is nothing but P into Q, which is public, and you calculate. You say you share N with everyone. There is no problem. N is your part of your public key. Next, after this, you calculate another one called as psi of N, which is nothing but P minus 1 into Q minus 1. This is the value of psi of N. Psi of N is nothing but P minus 1 into Q minus 1. Now, then you again choose or select a value E, which is public in nature, with the constraint as GCD, which is your greatest common divisor of E, and the psi of N which you calculated is 1. So the constraint of selecting E is that the GCD of E and psi of N must be equal to 1, and also E should be greater than 1 and less than psi of N. Once again, as I told you, E is a part of public key. So E can be public and it can be shared with others also. After getting the value of E, or after selecting the value of E, you have to calculate the value of D. D is part of your private key and should never be disclosed. You don't tell it to anyone. So D is equal to E inverse mod of psi of N. This can be written easily for our calculations as D into E is equal to 1 mod psi of N. This is the one which we use for calculations to finding out the value of D. As I told you, D is your private key. So just to reiterate, I need two prime numbers P and Q. Then I find out N is equal to P and Q. And then I also calculate psi of N, which is nothing but P minus 1 into Q minus 1. Of these three values, P and Q are to be kept private. I don't tell it to anyone. N can be public. So after calculating this, then I have to select a value called as E with two constraints saying that the greatest common divisor of E and psi of N must be equal to 1. And also E must be between 1 and psi of N. It should be greater than 1 and it should be less than psi of N. Finally, you have to calculate the value D such that D into E is equal to 1 mod psi of N. So your public key is nothing but E comma N, whereas your private key is nothing but D comma N. This public key is now shared to your user or whom you want to communicate with or to a group of users. This private key is kept secure. You don't disclose it to anyone. Okay, you can see this here now. Only the public key E comma N is published and all the other numbers involved, including your two prime numbers PQ, then the psi of N and D must be kept private. So the main property of this construction is that it is difficult to compute D from just the numbers E and N. Because if I am an attacker and if I am sitting on the network, I come to know what is your N and also I will know about your E. So I have with me what is E and what is N. So by looking at these two numbers and doing any type of cryptanalysis attacks that we discussed earlier, it should be impossible for an attacker to determine the value of D. That is the main constraint of RSA algorithm. Okay. See, there are many ways to do this. If I can start dividing N into its prime factors, then if I come across the values of P and Q, then I can calculate psi of N. And from the value of psi of N, maybe I can try and find out the value of D. So that is what I told you, factoring problem. The N value should be large enough so that determining P and Q should be impractical. It should take too much of resources. Now let me show you how this is actually implemented from these ingredients, how we do the encryption and decryption process. So this is what, as I told you, the first part is your key generation. So how does the user generate the keys? First, select both P and Q, both are prime and also P not equal to Q. Then calculate N is equal to P into Q. We discussed this. Calculate psi of N is equal to P minus 1 into Q minus 1. Select an integer E such that GCD of psi of N comma E is equal to 1 and E is greater than 1 but less than psi of N. Then calculate D so that D is equal to E inverse, or else we can say that D into E is equal to 1 mod psi of N. Hence, once we get all the values, I have the E value, I have the D value, and also I have the N value. So based on these three values, I publish my public key, which is nothing but E comma N, and then I calculate my private key, which I'm going to keep secure. This should not be disclosed to anyone. That is why we call it as private key, private only to the user. Now, let us assume that if there are two parties, A and B, isn't it? If there are two parties that wish to communicate. So here, both these parties, the first step that they have to do is, once if they want to implement this scheme, they have to create PUA and PRA. Similarly, B has to create PUB, which is nothing but public key of B and private key of B. Then these guys will be exchanging their public keys with one another. So A will send PUA to B. Similarly, B will share its PUB to A. Now A knows what the public key of B is. Similarly, B knows what the public key of A is. How do you use it? Now, if A wants to send some particular message to B, now if A wants to communicate something to B, what it will do is, it has to encrypt that message. Let us assume that A wants to send a message M to B. In that case, this M will be encrypted using the public key of B. Understood? And this message will be sent to B. Because once it has been encrypted with the public key of M, it can only be decrypted with the private key of B. because M has been encrypted with the public key of B, it can only be decrypted with the private key of B. So in this way, the confidentiality can be maintained. Nobody other than B or the intended receiver can open this message or can decrypt this message and read it. So this is what I'm going to do it now. Let me show you. The encryption part obtains the recipient's B's public key. So whatever B has published, E, N, I will receive it. And then whatever plaintext that I want to send, it is actually represented as a positive integer M with the condition that M must be greater than 1, but less than your value N that you calculated, P into Q. So your M must be less than N, but should be greater than 1. Then you have to compute the ciphertext C is equal to M power E mod N. This E corresponds to the public key of the B, which B shared earlier. This ciphertext is now sent to B. What is going to tell you that nobody else other than B will be able to decrypt this message, because B is the only person who has the control of the private key, or who has the private key of B, isn't it? Now let me show you the decryption part. So in decryption, if the B, whatever message that you are sending, the C will be received by B, and to decrypt it, what it will do? It will perform a decryption with the private key of B on the message, which is nothing but your C, which gives you your original plain text back. Understood? So uses his private key N, D to compute the plain text M is equal to C power D mod N. It extracts the plain text from the message representative M. So whatever M is got, it gets your plain text back. So this is the procedure. Both the parties first have to create the public keys and private keys, and then exchange the public keys with one another. After that happens, if I wish to communicate something with my receiver, I encrypt that message with his public key, send it over to my receiver. At the receiver, after receiving this ciphertext, because I am the person who is having the private key, the receiver decrypts it with its own private key and opens the message and decrypts the message, then performs the plain text conversion and gets it back. So this is the process which happens in the RSA algorithm. Similarly, Ulta process, if you want, if B wants to send something to A, what it will do? It has to encrypt with the public key of A, because public key of A is known to B. What it will do is E P U A of M, and this message will be sent by B, and only A can decrypt this message, because to decrypt it I need PRA. PRA is only with A. So this is how you perform encryption and decryption using RSA. Let me take some numerical examples and give you an idea, see how to get these things, okay, or how this encryption decryption process works. Let us go. So let us see that I'll start with simple examples, then we'll go for slightly complex ones. Let me assume that I have taken two prime numbers, P is equal to 3 and Q is equal to 11. So what is the next step that I have to do? N. N is nothing but P into Q, which is nothing but 3 into 11, that is equal to 33. What is psi of N? The third step is psi of N. What is psi of N? Psi of N is nothing but P minus 1 into Q minus 1. So P minus 1 is nothing but 3 minus 1. Q minus 1 is nothing but 11 minus 1. 2 into 10 gives me 20. So I now have the N value. I have the psi of N value. Now what to do next? We have to select a value called E. And the constraint for selecting E is that the GCD of E and psi of N. Psi of N is here is 20. So GCD of E comma psi of N is equal to 1. And also E value should be greater than 1 and less than 20. So here I am selecting the E value to be 7. Now the greatest common divisor of 7 and 20 is 1. There is nothing else. So this satisfies my constraint, and I have selected the value of E is equal to 1. Sorry, E is equal to 7. So from here until this point, I got my public key already, isn't it? What is my public key? Tell me. 7, comma, what is my N value? 33. So this is my public key. I have got it already. Next, after doing all these calculations, I have to calculate the value of D. I told you, how do you calculate D? D into E is equal to 1 mod 20. 20 is nothing but psi of n here. And the value of d should be less than psi of n. So to just get a feel of it, I'm just writing it down here. I know the value of E, isn't it? So 7 into D is equal to 1 mod 20. What do you mean by 1 mod 20? It can be either 21, it can be either 41, it can be either 61. So like that, just using trial and error method, if you start working on it, I can easily see that D is equal to, what is D? The D value is 3 because 7 into 3 gives me 21. 21 mod 20 is nothing but 1 mod 20. So this is just like a trial and error method basis through which you have to calculate the value of D. D is equal to 3. So you can see here 7 into D should give me 1 mod 20. In other words, you can write down, see what is 1 mod 20? What are all the possible values? 21 is one possible value. 41 is another one possible value. 61 is another one possible value. 81 is another possible value. Like that, you can keep on calculating. So here, I can just see that the first value is 7 into 3. So which gives me D is equal to 3. Now I publish both my public keys and keep my private key secret. So this is my public key which I send to all the users or to my receiver, and I keep my private key secret 3,33. Okay. Now I got my keys. The first part of key generation is completed. What's next? If somebody wants to send a message to me, what they have to do? They have to encrypt that message with the public key. So for that purpose, let us assume that somebody wants to send a message which is m is equal to 2 to me. And you have to also check that 2 should be less than 33 because my n value is 33 here. Understood? So the encryption part, as I told you, C is nothing but m power e mod n. So what is the value of m? 2. What is the value of e? E is have selected as 7. So 2 power 7 mod 33. What is 2 power 7? 128. So 128 mod 33 means 33, if you take the table, 33 3s are 99. So 128 minus 99 gives me 29. So this is the ciphertext that is to be transmitted. So if I am the user, I received a ciphertext as 29. I know that if I received the ciphertext, it has been encrypted using my public key. I have to decrypt it. So which key I have to use to decrypt it? My private key. So for that purpose, let me go to decryption part. In the decryption part, so decryption, how do I do it? M is equal to, tell me, your ciphertext to the exponential of my secret key and mod n. So 29 cube. What is 29 cube? See, there are two ways of calculating it. If you do it directly, 29 cube value is 24,389 mod 33. You can do it directly like this, or there is another way to do it. You can, what I usually do is I simply break it down into smaller numbers. So 29 square into 29 whole mod 33. So first let me find out what is 29 square. 29 square is nothing but 841 mod 33. That is equal to, what do I get? It is 16. 16 because 825 I have in 33. So in 16, that means that next I can put it as 16 into 29 whole mod 33. So 16 into 29 is nothing but 464 mod 33. That is equal to 2. So this is how you do it. You can actually do it in large numbers as well, or else you can simply write it down into smaller pieces. So which is equal to my m. See, I did the encryption, I got the same original plain text back. So let me take another example to show you. Okay. So let the plain text be. I am saying that same, I'm considering the same values. So let the plain text be m is equal to 14. In this case, once again, m power e. So m is 14. E value is nothing but 3, isn't it? E value is equal to 7. And, oh sorry, I have taken another value. E is equal to 3 here. Okay, let me take it. E is equal to 3 mod 33. So if I do this, I will get is 2744, which by mod 33, I will get this C is equal to 5. So I have selected another E value here. And I am so going to send C is equal to 5 to Alice. So based on that, once again, D comma N is 7 comma 33. I get the same thing. And C power D mod N. So if I do it, it is nothing but the ciphertext is 5 and the D value is 7 mod 33. So which will give me the original plain text of 14 byte. If you see, it is 78,125 and we revert back to the original plain text message, which is 14. So let me show you a slightly complex one, or let me take some other examples. So in an RSA algorithm, P is equal to 5, Q is equal to 11 are selected. Calculate the value of the decryption key if the encryption key is 27. What they gave is P is equal to 5. So they are telling me P is equal to 5 and Q is equal to 11. Okay. So I got both the values. So immediately I will calculate N, which is 55. And I can also calculate psi of N, which is nothing but 5 minus 1, 4 into 11 minus 1, 10, which gives me 40. Also told you the encryption key is 27. What do you mean by encryption key? It is a public key, isn't it? So the public key is 27. So PU is equal to, what do we get? 27, comma 55. The question is, they are asking to find out what the private key is. So for the private key, I need to find out the value of D, isn't it? What is the value of D? So D can be calculated using the formula D into E is equal to 1 mod psi of N. So if you put the right parameters, what is E here? 27 into D is equal to 1 mod 40. Similarly, as I told you earlier, what are all the possible values to get 1 mod 40? 41, 81. I think I need not look further, isn't it? In 27 table, if I see 41 is not possible, but 81 is possible, isn't it? So 27 3s are 81. So 81 mod 40 is nothing but 1 mod 40. So automatically I'll get D is equal to 3, which makes my private key as 3, comma 55. This is my private key. This is how you calculate the private key. That is what the question asked. Let us see another one. Using RSA algorithm, a participant AA uses two prime numbers 13 and 17 to generate the public and private keys. If the public key of A is 35, calculate the private key of A. So, okay, this is slightly large numbers. Let me take it. P is equal to 13. Q is equal to 17. And they also given me E is equal to 35. And the question says, what is the value of D? Isn't it? So, because I have P and Q values, let me first calculate N value. N is equal to P into Q, which is nothing but 13 into 17 gives me 221. Okay. Next, let us calculate psi of N. What is psi of N? Psi of N is nothing but 13 minus 1, 12 into 17 minus 1, 16, which gives me 192. So, I have my public key already. To find out the value of D, what do I have to do? D is calculated as, what is the value of E? 35 into D is equal to 1 mod 192. Now, if you are faced with such things, it's slightly large numbers. Don't get too confused or to get too frightened. If I were you, I'll see there is 192 here. So obviously it has to be a value more than 193 or something like that, isn't it? So if I take the 35 table, maybe 5 is not enough. 35 6 are. So let me just write down the 35 table here. Because this is a brute force approach. 210, 35 7s are 245. So in this way, I can keep writing it down. 8s are 35 8s are what? 35 8s are 280. Next, another 35 gives me 315, 9 to 9, and 10 gives me 350. That is also not sufficient. 35, 11 gives me 385, isn't it? So similarly, what are all the possible values that I can get here? I can get 193, and I can get 385, and I can get 577, so on. So you can see that in this particular table, 35 11s are 385, which matches the value. So I can simply write that. That means 35 11s are 385. 385 mod 192. I can write it down. 385 mod 192 is equal to 1 mod 192. Because we always write the remainder down. So for this purpose, I can simply say that D value is calculated as 11. Now, which gives me my private key value as, if somebody asks you what is the private key of A, you just simply can't write 11. You have to write both 11, comma, what is the value of N? 221. This is the private value. This is the private key. And similarly, you have the public key also, which is nothing but 35, comma, 221. In this calculation, if we need some bit of common sense, so just write down what are all the possible values, maybe 4 or 5 values. And similarly, looking at the size of this number, you can take the values here from here as well. Let me show you one other example, which you can use this. In a security system, Alice share her public key as 31, 247 and Bob's public key is. So that I have both the public keys. Alice received a confidential ciphertext message as C is equal to 58 from Bob. Decrypt it. Okay. Now to do this, I think we need Alice's private key, isn't it? Alice received a message, which is the ciphertext. To get the plain text back, I need to decrypt it. For decrypt, I need the Alice's private key. So that means I have to do the factorization problem, isn't it? Now, so Bob's public key is written down, and it's a confidential message. Okay. So in case, let me say that N is equal to Alice's public key is N is equal to 247. Alice's public key is 31, 247. So N is equal to 247. Now you have to start breaking this into prime numbers. Now, if I were you, what I would do is, what are all the prime numbers? 1, 3, 5, 7, 9, sorry, 9, not 11, 13, 17, like that, isn't it? So what, in that case, what I usually do is, I start dividing this. And if I start dividing this 247 into its prime factors, the first thing, 3 doesn't go, 5 doesn't go, 7 doesn't go, 11 doesn't go. If you get 13 into 19. If you just divide 247 by 3, 247 by 7, 247 by 9, sorry, 11, 247 by 13, you get 19. So the two prime factors I divided as P is equal to 13 and Q is equal to 19. Because I'm trying to I'm trying to find out what is Alice's private key. Bob's N is different. We don't need to worry about that. I'm just trying to get the values from here. Once I have P and Q values, then immediately what I would do is I'll find out what psi of N is. Psi of N is nothing but 12 into 18, which is your 216. So I have psi of N. Now I have to find the D value. So D, I have what is the E value? E is nothing but, it is already given 31. So 31 into D is equal to 1 mod 216. So what are the possible values here? 217 is one possible value, isn't it? So if you see 217, and similarly, we can start working on this. If you see here 217, this automatically. Now if I find 217, I can simply write D is equal to 7, isn't it? I have 217 by 31. 31 sevens are, it is nothing but 217. So automatically I can write down D is equal to 7, which gives me my private key of Alice is 7, 247. This is the private key of Alice. But they didn't ask me just the private key of Alice. They asked me to decrypt the ciphertext. So I have already received a message. Now what do I do? The message that I am going to get, or your M is equal to C power D
mod n, isn't it? So we already have the C value, which is given as 58. Okay. 58 to the power of D is your 7 mod 247. So once again, if it is a large number, please do not get frightened out. You just break it down into small numbers. You can write this as, if I were you, I'll take it into smaller numbers. 58 square into 58 square into 58 whole mod 247. So 58 square, if you do it with 247, what you do get is you get 153. So 153 into 153 into 153 into 58. Once again, you are getting large numbers. So what I would do is, I'll just find out the product of this, employ mod 247 on both the products, and then calculate. Then what I will get is, if I do this to mod 247, I get 191. And if I do these two and employ mod 247, I get 229. If I do it again, what do I get is 191 into 229 gives me 43,739 mod 247, which is nothing but 20. So if you understand, see, having large numbers should not scare you. You need to break it down into small things. So 58 square, 58 square. See, if you're good enough, you can simply write 58 power 4 into 58 cube. You can do that as well, no big deal. So here, your M, or the original message that is sent, is 20. So this is how you performed a decryption. We also performed a small simple factorization as well. It should be obvious that smaller numbers of n will not take much time to do the factorization. That is the reason, as I said, n size, the key size should be in around 1024 bits, or right now they are suggesting a key size of 2048 bits. That means more than 300 digits in length. I will show you. So this is another example which I brought from the Stallings textbook. So you can see this. It actually demonstrates how RSA can be used to process multiple blocks of data. Now, if you are the sender, and if you are having a message, this, how are you? And each alphabet is now converted into ASCII characters or ASCII values. So based on that, you have to encrypt this message, how are you, and send it over to the receiver. But the first things first, each user has to select the, or he has to generate the private and public key pairs, isn't it? So these are the some values which I have taken. P is equal to 73, Q is equal to 151, and E is equal to 11. So for this, they have to find out what the value of D is, isn't it? So see here, after finding out the value of D, I got it as 5,891. In the sense, your PU is equal to 11, 11023, and the PR is 5891, 11023. This you share with others. So whomever wants to send you a message, they have to encrypt their messages using your public key. So this message, how are you, is broken up into pieces. You can ask me, sir, why did you only take 2 pieces? Why can't you take 6? The reason is, I told you that there is one constraint on your message M. This is your message M, isn't it? Your M must be less than N. Your N is 11,023. It cannot be greater than N. So I have taken only 2 pieces here. So P1, P2, P3, I have broken it into blocks, and each block is subjected to the encryption using the public key. This is your public key. So after when you do the public key 3314 to the power 11 mod so and so, after all the calculations, you get this. So these blocks are concatenated and sent to the receiver. So at the receiver, these blocks are performed or subjected to the decryption using the private key. This is your private key. I have the private key. I do it once again, everything, and then you tally what you get. So you can see you get the same numbers as we hear. And once you write them down according to the ASCII values, get back at the receiver, you can find out that how are you is back. So this is how your RSA can be used to process multiple blocks of data. There is one other example which has been given in the textbook for RSA encryption and decryption processes. Once again, for a user to create the keys, it is given as P is equal to 17 and Q is equal to 11. Once again, the next thing what you do is n is equal to p into q, which is 17 into 11 gives me 187. Compute psi of n, which is p minus 1 is 17 minus 1, 16. Q minus 1 is 11 minus 1, 10. So which is 160. Then select E. So GCD of E comma 160 should be 1 and E should be greater than 1 and less than 160. So they have selected E to be 7. And determine the value of D such that D into E is equal to 1 mod 160. And D value should be less than 160. So if you can see, the simple equation here I get is your 7 into D is equal to 1 mod 160. Once again, if I were you, I'll start taking the values down here. The possible values are 161, 321. So if I take 161, I get here as 23. So if I divide this by 7, I get 23. So automatically I can select that D is equal to 23. You can see. Then once I get D value as 23, now I have both my keys available. I have my public key and also I have my private key. Public key is 7, 187 and the private key is 23, 187. D, N, E, N. Let us see what it is. Consider the message to be encrypted or transmitted. M is equal to 88. First, you have to verify that whether the given message M is less than your modulus or not. N is nothing but P into Q, which is 187. Then the encryption is calculated as C is equal to 88 power 7 mod 187, which is equal to 11. Now, if you ask me, sir, how did you get that 11? Once again, as I told you, if I were you, what I would do is I would break it into small pieces. Sir, how do you do that? What I will do is simply 88 square, because I try to put it into small numbers, into 88. This is how I do it. And first I will take the value of 88 square and then perform the mod 187 on that. So what is 88 square? 88 square gives me 7744 mod 187. If I perform the calculations of 187, I will get the value as 77. So which makes it here, if I implement, this is 77. If I do the same calculations on this, I get once again another 77. Same calculations, I get 77. And it is 88. Because 88 mod 187 is 88 itself. Now to make it simple, what I'm going to do is I'm going to break it into two pieces again. First, I'm going to calculate this, which is 5929. And this gives me 6776. And if I subject this mod 187 and this mod 187, so what I'll be getting is, for this 5929 mod 187 gives me 132 and 6776 mod 189 gives me 44. I multiply these two things, which I will be getting as 5808 mod 187. To do this, I'll get 11. See. So this is how you simply break it into small pieces and start working on it. A simple calculator is sufficient enough to do these calculations. Now, don't forget, this value is to be sent to the receiver now. At the receiver, you can see, at the receiver, you have to perform the decryption. Now, C is equal to 11, which is sent, and the receiver has a private key. PR is equal to what? 23, 187. To decrypt this message, the receiver has to use the private key. So C power D mod N. So C is 11, D is 23. So 11 power 23 mod 187 should give me 88. Don't think that I just put 88 here. I did all the calculations. Once again, if I were you, I will write down. Of course, it's up to you. You can actually go for 11 power 8 also. But for ease, what I did was 11 power 4 into 11 power 4 into 11 power 4 into 11 power 4 into 11 power 4. 5 4s are 20 into 11 cube mod 187. So I'll just did what the value of 11 power 4 is. So 11 power 4 mod 187 is equal to, I got 14641 which when I implement, when I reduce it in modulus of 187, gave me 55. So what I did was 55 into 55 into 55 into 55 into 55 into 11 cube, which is 1331. So what I did, perform on this, perform on this, perform on this. So when I did 55 into 55 modulus 187, I got 33. This is another 33. Here it is different. 55 into 1331 mod 187 gave me 88. So this 33 into the 88 gave me, so I did the multiplication here, which gave me 95,832 mod 187. You take a simple calculator, do the division, whatever quotient you got, multiply that quotient, then you can find the remainder, which gave me 88 back, which is the same as your original message. This is what we are working with, isn't it? So I got my original message back. So m is equal to 88. This is how you perform the calculations. So just don't get too stressed out or too tensed out when you see large numbers. Break it into small pieces and don't forget to reduce those things using the modulus value. Okay. So coming to the end with the RSA algorithm, as I told you, either both the keys can be used for purposes. Like I mean to say that if you want to encrypt it with the private key, then you have to decrypt it with the public key. If you want to encrypt it with the public key, then the subsequent private key must be used for decryption. So this makes this property of RSA, where I can use either of the keys for these purposes, makes it the most widely used asymmetric encryption algorithm for most of the applications that we use even today, like VPNs, financial services, bankings, UPIs, e-commerces, certificate generation, and other applications as well. RSA keys tend to be around 1024 or 2048 bits in length, making them extremely difficult to factorize. If you don't take my word for it, I'll simply show you an n value, which is a real value which is used in the practical world, and you can try to factor this out. This is the value of n, and if you are good enough, try to factor them into P and Q. If I give you P and Q, you can find out n. But if I give you n and I ask you to find out what is the value of P and Q, then it becomes really difficult to do that. So this is generally happening, and nowadays, recently, using this prime factorization method, some of the researchers were able to break the RSA key size of 768 bits. They have broken the n value, which is of length 768 bits, into P and Q values. But it took them more than 2 years and huge amounts of money and large computing resources. That is the reason NIST, what they did was, now they are actually asking everyone to use 2048 bit length instead of the original 1024. They are asking to increase the key size of to 2048. But most of the modern day applications with the current computing power that we have, they are already using 4096 bits of RSA encryption. And if you want to verify, this is the value of P and this is the value of Q. I got this from the internet. I don't have the computing resources to perform this calculation to get this out. Do check it out. Okay. So on a closing note, if you see this RSA and all the asymmetric encryption algorithms, the computations are very complex and they are very resource intensive. Obviously, when they're complex and resource intensive, they are slow also. So rather than you doing the encryption and decryption using an asymmetric encryption algorithm, it is always better to use asymmetric encryption algorithm like AES or triple DES or even DES, and use these asymmetric encryption algorithms to encrypt the session key that is used for symmetric encryption and send it. The best application of asymmetric key encryption algorithms is key generation, or is this particular encryption of the symmetric key that is used for the encryption purposes. So with that, so thank you very much for watching. And if you have any other queries on RSA, there is I will try to make another video on how RSA can be attacked. What are the different ways through which RSA can be broken down, or the different cryptanalysis attacks that are possible on RSA. So till then, thank you very much and
Do take care. Good luck.